Hi.
Hi, are you sure this course is just for 2499?
Yes, and you know this is the only course with this expertise across the world.
No way!
Yes way. Don't delay. Enroll now.
Geeks learning together.
Hi.
Hi, are you sure you can prepare for product based companies through this course?
Yes, sitting at home?
No way!
Yes way. Don't delay. Enroll now.
Geeks learning together.
Yes.
Hey, what do you mean by a self paced course?
Well, the course material is available in the form of video lectures. And there are multiple practice problems that come along as well. So, you can access all of it anywhere, anytime. And they are available to you for lifetime.
No way!
Oh, yes way. Don't delay and enroll now.
Geeks learning together.
Yeah, so hello everyone. Very good evening to everyone who are present here right now. And I would request you all to kindly write your name in the chat box or just do a +1 for confirmation that you are listening to me right now. And then we can very quickly start. And also just confirm me that my voice is properly audible and I am properly visible. Okay, so I'm sharing my screen as well, and then we can very quickly start. Am I properly audible? And I would request you all to kindly do a +1 in the chat box. Okay, so let us wait for a couple more minutes for other students to join and then we can very quickly start. Yeah, audiences are coming in right now. I would request you all to kindly do a +1 in the chat box just for confirmation that you all are watching with me right now, because I would like to keep the session as interactive as possible and it will be enjoyable for you as well and for me as well. Hello Rishit, how are you? Rishit, I remember you were there in my yesterday's session as well. Hello Saurabh, how are you? Okay, so yesterday we studied about essential mathematics topic which are frequently asked in coding rounds as well as in interviews. So today we will be continuing the same as well. And yesterday we studied about binary exponentiation. Today we will be looking into one more form of multiplication called binary multiplication. Okay, and we will also be looking into prime numbers and how to check for prime and Seymour-Wiener algorithm. Okay, hello Abhinav, how are you? So let me present my screen and then yeah, we have around 5 people live with me. More students will be joining as the session progresses. Okay, so okay, yeah. So let me give you a small introduction about this of last session. This is a continuation basically. So today we will be discussing about binary multiplication, and we'll also be discussing about prime, how to check for a prime number and how to generate prime numbers and prime factors. Okay. So these are topics not related to each other, but you can just listen to me, and later onwards you can know more about these topics. Okay. So if you have any basic foundations of mathematics, you will be able to understand and go along with me. Okay. Saurabh, is that helpful? Yeah. So let me give you a small introduction about this session. So this session is basically a practice session for SDE interviews, and we every week for 2 or 3 days I will be going live here, and we will be discussing most of the important concepts and topics and questions which are very frequently asked in interview these days. Okay. So the topic for today's discussion will be essential maths, and which we discussed yesterday as well. Okay. So I hope my screen is slide is properly visible. Hmm. And also one more thing, you will be able to see a link for a course called Complete Interview Preparation in the description of this streaming, and as well as on the it is pinned on the first comment. So if you are someone who are targeting an interview upcoming interview season, so you can definitely check out that course. It is one of the really well crafted course for interview preparation, and means that course contains all the important concepts and all the important questions which are frequently asked in interviews. Okay, so I would highly recommend you all to watch that, have a look at that course. Okay, and apart from that, we also have a live mock DSA session on every Saturday at 10 p.m. on this very channel itself. So if you would like to have your interview scheduled, or if you would like to have a practice mock interview with any of the mentors at Geeks for Geeks, you can sign up for that session, and we will try to schedule you. Okay, so this was about the live mock DSM. So let us come back to our topic of concern today. Last Saturday there was no mock, right? Yes, last Saturday there was no mock, right, due to some technical issues. uh, okay, but we will try to do it this Saturday as well. Okay, actually, those mock DS are quite interesting as well. Like, students are highly motivated to give a mock interview live in front of YouTube, in front of live audiences, and it will actually be quite a useful test for your preparedness as well. Yeah, welcome, Rashid. So let us start then. So let me give a small introduction about myself. My name is Gaurav Kumar Shaw. Let me write it on the screen. And I am presently in my third year of BTech at IIT Kharagpur. Okay, and I'm also a mentor at Geeks for Geeks. Okay, and I'm also an incoming. Okay, so this is about me. You can try to look me up in LinkedIn as well if you would like to connect with me. And apart from that, let us start with our topics here. Yeah, so yesterday we studied about binary exponentiation. Okay, so let me just do a small revision. So yesterday when we studied about binary exponentiation, it was basically a method to compute a to the power b. Okay, in log n complexity. I hope everyone remembers about how to compute a to the power b. We discussed why the power function would fail, and why if we would like to compute large numbers of a and b when both a and b are up to 10 to the power 8 or 9. In that case, this was quite helpful. Okay, so that method gave us the power a to the power b accurately in a complexity of logarithmic complexity. Okay, so this was about binary exponentiation. The constraint for binary exponentiation was that in A and B, A should also be less than 10 to the less than equal to 10 to the power 9, and B should also be less than equal to 10 to the power 9, because A and B will fit inside an integer. Okay, so this was a question. Now the question arises: what if A is up to 10 to the power 18, and what if B is also 10 to the power 18? In that case, what will happen? Will binary exponentiation work? Because it will in that case, what will happen, binary exponentiation will no longer work. It will give you incorrect result, because a and b are itself very large, and you will not be able to store in integer data type. And in fact, even if you store in integer data type, what will happen, still it will give wrong results. Okay, I will show you how. Okay, so in that cases, we have to slightly modify the binary exponentiation and introduce something called as binary multiplication as well, to compute these during these conditions. So the first condition is actually very easy. What if a is less than or equal to 10 to the power 18? Okay, that is a increases. Initially a was up to 10 to the power 9. Now a is up to 10 to the power 18. So in that case, what are we supposed to do? And initially also in binary exponentiation, we used to take a modulus, right? that whatever results you're computing, take it modulus of m, and m always used to be 10 to the power 9 plus 7, which is also which can also fit inside an integer data type. Now you are asked to take a to the power b modulo m, given a is up to 10 to the power 18. Now what will happen? Since a is up to 10 to the power 18, this may give a wrong result if you follow the binary exponentiation rule. Okay, so what will you do? Any ideas? Yeah, I would request all of you all to kindly keep the session interactive by writing your doubts in the comment, and whatever I'm asking here, you would reply your answer in the chat box. Okay. Hello Saurabh, hello Rishit, hello Abhinav. Are you all still there with me? I would request you all to kindly stay with me till the very end, because this concept would prove very extremely important for you all. Okay. So the question that I'm posting right now is that. So the question that I'm posting right now is that if a is up to 10 to the power 18, then what is the binary exponential will definitely give us a wrong result. So in that case, yeah, can we try mod 1 10 to the power 18? Yes, we will try. In that case, we have to use concepts of Euler-Torsson function. That is a bit advanced, and we won't be discussing here right now. Okay. So the first condition is that what if a is up to 10 to the power 18? Next condition is what if b is up to 10 to the power 18? And the third condition is what would happen if m is also 10 to the power 18? Okay. So since Rishit, you are asking that what if you try to take mod of 10 to the power 18, right? See, basically, you will be taking the modular, but not with 10 to the power 18. You will be taking modular with the help of 10 to the power 9 plus 7. Okay. So let me show it to you. Since computing a to the power b involves, okay, I'm writing it here. Computing a to the power b involves multiplying a b number of times. Okay, okay, you are multiplying this b number of times. Now I'm asking you to take a modulo m with this expression. So what if you take modulo with individual of a? Okay, in that case, what will happen? Since m is up to 10 to the power 9 plus 7, a modulo m will become less than equal to 10 to the power 9. Okay, so it will try to go within 10 to the power 9, which is the constraint of integer data type. So if our a becomes large, that is, uh, if in a to the power b, a becomes large, what we will do basically, we will do something like this. We will just take a mod m, then we will compute binary exponentiation, and then modulus of n. Okay, so this will be the result. So now we have a question. What if modulo m? M is up to 10 to the power 18 plus 7. In that case, what we will do? Okay. In that case, what will happen? If you are trying to take a modulo of m, it won't affect much, because a into a is up to, since a is a 10 to the power 18, a is also 10 to the power 18, and if you are trying to multiply, it will overflow long as well. So in that case, it won't work. So for that, we have to use a concept called binary multiplication. Okay. Now, it is binary multiplication is based on the fact that if a is up to 10 to the power 18, then a plus a is also up to 2 into 10 to the power 18, which you can basically store in long data type. Okay. And once this is up to 10 to the power 18, you can easily take a modular with m, and then you can repeat the entire process. Find the value of a whatever times you are trying to multiply a. Okay. So I hope is the concept here. Why don't we use power function? That is a very good question, Sachin. So can anyone tell me why don't we use a power function? I told this concept in the previous session. Anyone in the audience can clear Sachin's doubt. That would be very helpful. So the thing that the idea that was posed by binary multiplication is that instead of multiplying two numbers, I will just add them that particular number of times. So if it is required to multiply a into a, instead of multiplying a into a, I will add a number of times. That is, I will do a plus a plus a plus a plus a up to a number of times. Okay, but why we are doing this? Because addition is easy. Because if we are trying to add 10 to the power 18 and 10 to the power 18 together, this will give me 2 into 10 to the power 18, which can be stored in long. Okay, but 10 to the power 18 into 10 to the power 18 will give you 10 to the power 36, which you cannot store in long. Okay, so you can add. So instead of multiplying, what you will do, you will add the numbers and then take a modulo m. So what will happen at every step, your number is well within 10 to the power 18. That is well within long data type. Okay, but the time complexity of this operation would be O of n, and this is a not optimized. This is not an optimized approach. Instead, we need log n, because binary exponentiation was giving you result in log n time complexity, and linear time complexity would prove to be quite costly in this case. So therefore, you need log n complexity for solving this question. So Sachin, basically why we don't use power function is that, as I told in the previous session, what happens is power function returns a double data type. Okay, now double is actually a very good data type. It can actually help you store quite a large number, but it doesn't store them accurately. For example, if you would like to store a large number, let's say 10 to the power 22 in a double data type, then what it will do, it will make sure that there are precision errors. So it will not store exactly 10 to the power 22. It will store a little bit less number than that. Okay, so since power function return double data type is unable to store exact answer. Okay, that is the reason we do not use power function while we are doing comparative programming. Okay, but for smaller number, like if you're trying to compute 2 to the power 3, in such cases you can easily get using power function. But the idea to learn such methods like binary exponentiation, binary multiplication is that when you are doing comparative programming, what happens, you get constraints which are very high. Okay, and in such cases you have to make sure that your answer is quite accurate, because the submissions are checked using the results provided by the online judge. So basically they have to match exactly. So there should not be any scope of error in such cases. So that is the reason we are not using power functions, and we are relying on such concepts of mathematics to solve it. Okay, yeah. So now the idea is, what is binary multiplication? So binary multiplication is basically a function that will help you compute a multiplied with b. Okay, that will help you compute a multiplied with b. Hmm. So let's say you pass two numbers a and b into this function. Initially, you keep answer equal to 0, and first you check if b is greater than equal to 0 or not. If it is greater than equal to 0, in that case, what you will do, you will basically check if b is odd or not. If b is odd, what you do, answer is equal to answer plus a, and then you take a modulo of m, and then you make a is equal to a plus a modulo of m, and then you decrease b. Why this was so? Let me tell you this. For example, let's say you want to multiply 3 into 13. So first of all, you have to represent 13 in the form of binary. Binary of 13 will be 1101. At the 0th position, we have a 1. At the first position, we have a 0. At the second position, we have a 1. And at the third position, we also have a 1. So what is this doing? First of all, we are checking. This is basically a check for whether the last bit is set or not. If it is set, then only we are adding that answer. Okay, because see what is happening here. Instead of multiplying 3 into 13, what we are doing, we are multiplying 3 into 2 to the power 3 plus 3 into 2 to the power 2 plus 3 into 2 to the power 0. Okay, so we are skipping the first position because that is being multiplied by 0. So I am only interested in these values. Okay, only types of multiplication I want to do. So what I'm doing here, I'm taking answer equal to 0, and I'm adding answer to a only when I have a set position. Okay, so initially we have got this is a is equal to 3 and b is equal to 13. Okay, so initially we got a is equal to 3, so answer will become 3. So because at the first position we have a set bit, so this 3 is coming here. Okay, now what will happen, uh, this will now a will become a is equal to a plus a. So a will become 3 plus 3, a will become 6. Now what will happen, b is right shifted by a bit position, therefore b will become 13 divided by 2, that is equal to 6. Now b becomes 6. Okay, now in the next iteration, what will happen, we will check whether b is the last bit is set or not, but we are standing on this 0, so it is unset, so this statement won't get executed. But now a will become 6 plus 6 equal to 12. Okay, now a will become 12. Now once a becomes 12, what I will do here, b will once again get divided by 2, and b will become 3, so it will become 1 and 1. Now again, when since b is odd, it is equal to 1. What it will do, it will add answer plus a. So answer was initially 3. Okay, now it adds 12, because a has become 12. So 12 plus 3 is equal to 15. So now my a become 15. So this is basically 12. This is basically 3. Okay, And finally again a will become double, that is equal to 12 plus 12 24, and this 24 is exactly this, 8 into 3 is 24. So again this will become added, so 3 plus 12 plus 24. So in just 3 additions we are able to solve the question of 3 into 13. Okay, if we had been following a linear complexity this would have taken 13 iterations, but in just we are doing it in 3 iterations. So this is nothing but equal to 3 into 13 with the help of binary multiplication. I hope this is clear, the concept of binary multiplication. Can I please have a +1 in the chat, those who have understood the concept of binary multiplication? And if you have any question, you can ask me. Can we take one more example? Okay, Rishit, let me take one more example. Uh, okay, so first of all, let me take a new slide, an empty slide, and we are in fifth slide. We'll start a failure. Okay, yeah. So what we are doing? We are doing binary multiplication. We saw how we multiplied 3 into 13. Let us now try to multiply 2 into 17. Okay. Or let's say we try to multiply 5 into 19. Okay. 5 into 19. So what is 5 into 19? Can anyone tell me? Why we mod m? Okay, so Sachin, you are asking why we do a modulo m. Okay, because a is up to 10 to the power 18, and we want to keep all the numbers less than 10 to the power 18. So if at any point of time the value exceeds 10 to the power 18, we don't want that, because in such cases it will not fit in long data type. So that is the reason we have to always make sure that we are taking modulo of m at every point of time. Okay. So just to make things fit in the particular data type, we have to take a particular modulo. Okay, so let's see binary multiplication. So now we have to calculate 5 into 19, that is 95. Can you all please write the binary representation of 19? Anyone who can write a binary representation of 19? Sachin, Saurav? Tell you all right, let me just write the algorithm in a small bit. Okay, yeah. So binary is 10011. 100. Sachin, you are writing a bit different. 95, it should be 10011. Okay, 10011. Okay, we can just confirm it will be 2 to the power 0 is equal to 1. 1 plus 2 plus uh, 16. It should be 111 plus 8. 25 and finally 1011111. It will be uh, yeah, 19 will be 10011. Okay, so this will be the binary representation of 19. Yes, Saurav, you're correct. 10011. Okay, yeah. So now we see that at the 0th bit it is set, at the first bit it is set, at the second it is not set, at the third it is not set, and at the fourth it is not set. Okay. So what we will do basically, instead of saying that I have to multiply 5 with 19, also I can also say that I am multiplying 5 into 2 to the power 4 plus 2 to the power 2, 2 to the power 1 plus 2 to the power 0. Because only at the 0th bit, first bit and the fourth bit we have the binary representation to be set. Okay, so I can say this. Now I'm writing three variables. First I'm writing A, uh, hmm, answer variable, B and A. Okay, so let me write something like this: A, B, and the answer variable. Hmm. Okay, the answer variable A, B, and answer. So A, B, and answer. Initially, what is the value of A? The value of A is 19. The value of A is 5. B is 19. Okay, and answer is equal to 0. Okay, this is the initial part. Now what happens, we come inside this loop. B is greater than 0, yes. Now we check if B is odd or not. In fact, checking this basically means whether the last bit is set or not. So it is set. So in that case, what will happen, we will come inside this if condition. Then what we will do answer is equal to answer plus A. So initially answer was 0 and A was equal to 5. So answer becomes 5 in now. And finally, what is A becoming? A is equal to A plus A. So A is becoming 10. And what is B becoming? B is equal to B divided by 2. So 19 divided by 2 becomes 9. Okay. So after the first iteration, my value of A is 10, B is 19, answer is equal to 5. Now I come to 9. Now when I come to 9, I again see that the last bit is set. So now what will happen? My answer will become answer plus A. So answer was 5, A was equal to 10. So in that case, what will happen? 10 plus 5, answer is becoming 15. Answer is becoming 15. A is becoming A plus A. So 10 plus 10, 20. A has become 20. B will become 9 divided by 2, that is equal to 4. So B has become 4. Okay. So this was after the second iteration. Now tell me, what will happen after the third iteration? I hope everyone is following with me. What is inside if condition? Okay, Sachin is asking what is inside if condition. Inside if condition, I have written A and 1. So A and 1 is a bitwise way to check whether B is odd or not, or in fact it is checking that whether the last bit or the last bit of B is set or not. If the last bit of B is set, it will return true. Okay, and if it is not set, it will return false. It is same as checking whether B is odd or not, because in an odd number the last bit is always set. Okay, so because the reason why we are doing this, I have to only multiply that particular value of 2 to the power something if and only if at that position I have a 1 in the binary representation of B. As you can see, in the binary representation of 19, I have 1 at the 0th position, at the first position, and at the fourth position. So whenever I am going to that position, I will only I will only update my answer variable, because I am multiplying. First of all, I have to multiply 5 into 1, then 5 into 10, that is equal to 10 plus 5, 15, then again 5 into 16. Okay, 2 to the power 4 is 16. Okay, so I have to make sure I am doing that. That was the reason I am checking with B and 1. Yes, Saurav has written it very perfectly. 10011 and 1 will check if last bit is set or not. Okay, thank you, Saurav, very much. So I hope, Sachin, the doubt is clear. Okay, so let us continue then. Now, since we are left with, yeah, now we are moving to the third iteration. So when you are moving to the third iteration, what becomes here is that, so now what will happen? Huh. So third iteration, B becomes 4. Now B and 1, this condition will fail for B equal to 4, because 4 is an even number and the last bit is 0 and it is not set. So in that case, this condition will fail. So we are not updating our answer in such condition, because I just encountered a 0 bit. So for every time we are encountering a last bit to be equal to 0, I am not updating my answer variable. So for the fourth iteration, my answer will remain 15. Then what will be the value of B and E? But A will continue to get updated. A will be equal to A plus A. So 20 plus 20 will become 40. B will become divided by 2, that is equal to 2. Okay, this is done. So again, I will repeat the same process. This time B is equal to 2. But again, what will happen? This b is equal even number, so this if statement will not get executed. Again, a will get updated. So a will get updated to a plus a, that is equal to 40 plus 40 is 80. So now my a is becoming 80. So let me write a here. So a is 80, and finally b is becoming 1. Okay, and my answer will stay as it is 15. Okay. Now in the last iteration, what will happen? It will check whether b is odd or not. Since b is equal to 1, it is an odd number. Now my answer will get updated to answer is equal to answer plus a. So 15 plus 80. So what is 15 plus 80? 15 plus 80 is 95. So my answer will become 95. Okay. Now my a will become a plus 8. 80 plus 80, 160. So a is becoming 160. B is becoming 1. Right shift 1 will become 0. So now b is becoming 0. So what will happen? The condition of the while loop, this will become false now, and we are coming out of this loop. It means that we have successfully done the binary multiplication part, and whatever remains in our answer is our answer. So 5 into 19 was 95. Okay. So in this example, the while loop is only running log n number of times. Instead of if we had done it linearly, we have to go across a loop of 19 times. So we have to add 5 into 19 is 5 plus 19 times. But in this case, we just did it log n number of times. Okay, those number of time in which the number of bits are there. In 19, we have 1, 2, 3, 4, 5 bit positions occupied. So in such cases, we only did 5 iterations only for solving this problem. Okay, instead of doing 19 operations. So this is the advantage of doing binary multiplication. Okay, I hope everyone understood it. Hello Naikaj, how are you? I'm seeing you after quite a lot of time. Hmm. So Naikaj, we are currently, why do we, Rishit is asking that why do we do a is equal to a plus a modulo m even if the last bit of b is not set? Okay, see, if the last bit of bit is set, in that case, I am updating my answer variable. If it is not set, I am not updating my answer variable. But I have to update my a variable. Why? Because a has to keep on updating. Okay, since I am multiplying the value a, initially a was 5, then it become 10, then it become 20, then it become 40, then it becoming 80. Okay, because a has to get doubled because I am moving from one bit position to another. When I am at the 0th bit, a is equal to whatever value of a it is. Now, when the first position, a has to get doubled because I am moving from one bit to another. If it is not set, I am just not updating my answer variable, because updating answer variable means that I am actually doing the multiplication. So if it is not set, I'm not supposed to do the multiplication. I am only supposed to do the multiplication only at those positions in which the bit is not set. Okay. I hope you got it, Rishit. Okay, so is the dry run very clear to all of you? Yeah, thank you, Rishit, very much. So is the dry run clear to you that how we are getting 95 and how the is the complexity of binary multiplication to be equal to log n? Hmm. Okay, so let us move to the next part of our discussion. So yeah, now we studied yesterday about binary exponentiation. So what we were doing in binary exponentiation is that, so we had our binary exponentiation function. We used to take two variable a and b, and initially our answer was equal to 1. If b was equal to what we used to do, we used to multiply answer into a. It is similar to how we were doing binary multiplication. But now what we will do, we will, instead of doing answer into a, because answer into a, we will just do binary multiplication of answer into a. And a is also binary multiplication of a into a. So we are just utilizing this function we had created. Okay, so what will be the time complexity of this? The complexity for this function is log n, and the complexity for this function is also log n. So the complexity will become log of log n. Okay, so this is the complexity of binary exponentiation in cases where we have to use binary multiplication. Okay, so this was about binary multiplication. Yeah, and it is all for those condition in which we had to basically take the modulo m, and modulo m was 10 to the power 18. Okay, so we could not actually multiply a into a, because a into a would become 10 to the power 36, which will basically fail. So that is the reason we had to use binary multiplication, and we could not do it linearly, because if we were doing it linearly, the complexity would become n log n, and we don't want that. So we utilize the concept of binary multiplication. I hope this part is clear, very crystal clear to everyone. Can anyone please summarize me that the main importance of binary multiplication in binary exponentiation? I'm writing that in a separate slide, just such so that you can understand. So the thing was that we were doing a to the power b using binary multiplication. This is a summary slide. Okay, binary exponentiation, which we studied yesterday. In this case, a and b were up to 10 to the power 9. Okay. Now what happened? Uh, we also required to take modulo of m. So now if m becomes 10 to the power 18, in such cases, we have to use binary exponentiation with binary multiplication. So the complexity becomes log of log n. Okay, the complexity of this code was just log n. When m becomes 10 to the power 18. In this case, m was also 10 to the power 9. So this is the thing which we studied yesterday. This is what we are studying right now. Okay. Yeah. So now let us look into the concepts of. Hmm. So now let us look into the concept of prime numbers. Okay. So I'm sure that everyone knows about the definition of prime numbers and what are they. So prime numbers are basically those numbers. Let's say n is a given prime number. So we can call a prime number if it contains only two divisors, one and the number n. Okay. Now we have to do a prime check. Now for I equal to from 2 to n minus 1, if n mod I is equal to 0, in such cases what we will do? We will write is prime equal to false, and then we will break out. So if any number has a divisor which is not 1 and not n, in such cases we will call it is not a prime number. So this is a simple loop to check whether a given number is prime or not. But the complexity is O of n, and we don't want that. So we have to improve upon this complexity. And how we will do that? Let us see. So one thing we can observe is that instead of going for entire 1 to n, 2 to n, what we can do basically, we can just go to square root of n. Because if I'm checking whether a number is divisible by 3 or not, if it is divisible by 3, it means that it will also be divisible by the next part of 3, that is equal to 12. Let's say number is 36 is divisible by 3. So 36 divisible by 3 is 12. So 36 will also be divisible by 12, and it will give me 3. Right. So this part should be clear. So instead of checking for 2 to n minus 1, I can just check for square root of n. So I can just write this loop. So it is actually an optimized version from than the previous one. Although it is not a highly optimized version, but it's still a bit of optimization is there. So we are doing the square root of n. The complexity becomes square root of n. Okay, but this is also not a very good idea. We have to make sure that we are doing it in a better way. Okay, so now we come across this concept, how to store prime factors. Okay, so let's say we got a number 36. 36 has a lot of prime factor. It has 2. 36 is 9 into 4. So 2 square is 4. And 3 square is 9. So 9 into 4 is 36. So the prime factorization of 36 will be 2, 2, 3, 3. Okay. So you want to store all the prime factors in a vector. How will you do that? So we can do something like this. This Let me see. Is there summary is clear? Yeah, thank you, Rishit, very for your kind words. Yeah. So does anyone know how can we actually find the prime factors? Yeah, so those who have joined late, I would request you all to kindly do a +1 in the chat so that I could know your name and just to mark your presence. Apart from that, we have something called as complete interview preparation course. You will find the link attached in the description and at the same time in the first comment. So you can definitely check that out if you are preparing for your upcoming interviews. Okay, so let us see. So how exactly we will store the prime numbers here? So we will be utilizing this concept that the smallest divisor of any given number will always be a prime number. Okay, so the smallest divisor of any given number is a prime number. So the smallest divisor of 36 is 2. So 2 is a prime number. So what we are doing, we are starting from 2, and when we are talking about smallest divisor, we are not taking into account of 1. Okay, we can get the prime factor using a sieve. Yes, we will. I will move to sieve concept after this. Okay, so. So what we are doing basically, first of all, we are getting a number 2 and we are iterating across while n mod I is equal to 0. So I am just dividing the number n by I. So if I am getting 2, I will divide 36 by 2. Then again, whatever number I will get, I will again divide that by 2. Okay. So I'm removing all the 2's from my given number, all the factor 2's from my given number. And at the same time, I'm storing it inside a vector called prime factors. So first I will get 2. So 36 mod 2 will give me 0. I am pushing my 2 into my prime factor vector. And again, I'm doing n equal to n divided by 2. Okay, so this will keep on running and I will get all the prime factors. Okay, so this will run for 2, I will get 2 2's. Then this will run for 3, I will get for 3 3's. Okay, and later the onward I won't get any values because n mod I won't be equal to 0. Okay, so the complexity is of this code is still O of n. Okay, finding all the prime factors of a given number in linear time complexity. We can optimize that by writing I square is less than equal to 1, but there is a small error in that. In that case, it will be that if the final number which I'm getting n is equal to greater than 1, in that case what will happen? I have to push back that particular number. Okay. For example, let's say I have to write 24. 24 is 8 into 3. So all the 2's will get stored, but finally when I'm having 3, so what will happen here? Huh. So I'm not running, I'm only running till root of 24. Okay. So initially it is checking till root of 24. So initially it will check for root of 24, but again I am dividing n by 8. So 24 divided by 8 will become 3, and root of 3 is equal to 1. So this will I will just this loop will come out of it. So if after I have done this operation, if n is greater than 1, in that case I will push back into my prime because n is a prime number and it should be added. Okay, so this is the concept. So from linear time complexity, I just improved it up to square root of n time complexity. So I hope everyone understood the second concept which I was trying to tell. Okay, Saurabh, thanks a lot. So now let us look into the concept of sieve. Okay, now why sieve is necessary? So basically, sieve is actually a very important concept because using sieve, you will be able to solve quite a lot of problems, and sieve is, and modifications of sieve are extremely useful while you're dealing with different types of problems. Okay, so let us talk about sieve then. So sieve is basically a way to consider to store all the prime numbers up to a given value n. So let's say I want to know all the prime numbers from 1 to 30. Okay. So this will happen in a much better time complexity than linear. So instead of no, it's not like that I will just go across from 1 to 30 and check whether it is prime or not. That will be highly computationally very expensive. So we will utilize the method of sieve. So what is the sieve doing? So let me just say that I have listed down all my numbers from 1 to 30. So the first thing that sieve assumes is that let us consider that all the numbers are prime. So all the numbers from 1 to 30 are prime. So in that case, what will I do? Initially, I will strike out the number 1 because 1 is not a prime number. Then I will start with 2. So I am assuming that 2 is a prime number. So since 2 is a prime number, I will strike out all the numbers which are multiples of 2. So I have struck out 4, 6, 8, 10, 12, 14, 16. In fact, all the even numbers will get cancelled in the first iteration only, which is basically half the numbers. Then I am landing on the number 3. So I have to again strike out all the multiples of the number 3. So the multiples of number 3 would be 6, which is already striked out. It will be 9, then it will be 15, then it will be 21, and then it will be 27. Okay, so then I am coming to 5. So all the unstriked letters are basically numbers, are basically my prime numbers. So now when I am on the number 5, I have to check all the multiples of 5. So 10 is already striked out, 15 is striked out, 20 is striked out, 25 is not striked out, so I strike out 25. 30 is also striked out, so 5 is done. Then I come to 7. Now 7 multiple 7 would be 14 is striked out, 21 is striked out, and 28 is also striked out. So 7 is a prime number. 11 is also a prime number. The multiple of 11 is 22, is already striked out. 13 is a prime number. The multiple of 13 is 26, is also striked out. 17 is a prime number. The multiple of 17 is 34, which is not in the list. 23 is also a prime number. And finally, 29 is also a prime number. So whatever number remains which are not striked out is basically my prime numbers. So I have done this computation, I can say, in a much, much, much better time than linear complexity, this operation. So what I'm doing, initially I am considering all to be prime number. I'm striking out 1, and then I am striking out all the multiples of 2, then I will do 3. And if after I do this for all the numbers, whatever number remains is basically a multiple, are my prime numbers. So first I'm checking whether it is striked out or not. If it is not striked out, it means it is a prime number. And if it is a prime number, you have to strike out all the multiples of the prime number, because if a number is prime, the multiples of that particular number can no longer be prime. The concept of sieve is just based on this concept. If a particular number is prime, all the other multiples of that number won't be prime. So I suppose this part is clear. Now let us look into the complexity of sieve algorithm. So let us suppose that you are given a question, that you are given a query up to 10 to the power 7, and for each of the query you are given a number n, and you have to find whether n is prime or not. So what you will do basically, if you are doing by if you are doing this by the normal computation, it will take 10 to the power 7 multiplied with square root of 10 to the power 7, which is 10 to the power 10.5, which is extremely high number. So this is computationally very expensive and it won't pass in 1 second. So the optimized version would be to generate all the primes up to 10 to the power 7. So by using the sieve algorithm, you will generate all primes up to 10 to the power 7. And after you generate all primes, you can just run a query loop, and inside all O of one operation, you can give results for all the 10 to the power 7 queries. Okay. So this is in such problems when you are required to do something inside a query, or the computation is becoming very expensive, you have to utilize the sieve algorithm to store all the prime numbers up to a given value n. Okay. Now the time complexity of sieve algorithm is actually very less. It is log of log n. Okay. So time complexity of sieve is log of log n. I will just show you how this is coming. Okay. So let us see then. This is a code for sieve algorithm. So you declare a number called end. N is a number until which you want to find your prime factor. All the prime numbers up to a given value n. Okay. So I hope everyone is following me. Can you please have a plus one in the chat if you have just understood whatever I've explained till now? Thank you, Saurav. Thank you, Rishit. Are you there? Okay, Rishit. Thank you very much. So yeah, so this is the code for prime. How to find the number of primes till the number n. So let us say that you are storing a vector called boolean in that called s prime, and the size of that vector is n, and you're initially marking it as 1. So it means that the initial assumption of C was that, let us assume that all the numbers are prime. So that is the reason you are putting 1. 1 means yes, it is a prime number. So basically is prime of I, if it is true, it means that it is a prime number, and if it is false, it means it is not a prime number. Okay, so after that you have to just rely on this function. is prime, is this vector, Boolean vector. The first step would be to disregard 0 and 1, because 0 is not a prime number and 1 is also not a prime number. So we just mark them as false. This is what we know. Then we run a loop from 2 to n. Okay. And then what we are doing, if is prime of I is equal to true, if the value at that particular position is not striked out, it means that it is true. Then what you will do, you will run a loop from 2 into I less than n, j plus equal to I, and you make it false. So initially I will be equal to 2. So what you are doing, 2 was not striked. So all the multiples of 2 will be striked. So this loop is basically striking out, that is striking out all the multiples of I. Okay. So this is the concept. Okay, I will just explain. I hope this is clear. So what will be the time complexity? Can anyone tell me how the time complexity is coming out to be log n log of log n? This will be n into log of log n. So what we are basically doing is that, let us say that we remove the if condition. This is the if condition that we are checking if is prime is equal to true or not. So if is prime is equal to true, in that case what will happen? I will go for 1 by 2, 1 by 3, 1 by 5. So I am doing for n by 2 operation, n by 3. Loop is running for n by 4, n by 5 up to n by n. So this comes out to be n into log n. We are taking n common, and this term is basically log n. And if condition is mentioned, in that case I am doing for all the prime numbers only, because the condition is that I will only run the second loop, the nested loop, only if and only if that I is prime, I is a prime number. So for that case, this expression is equal to log of log n. Okay. So the overall complexity becomes n of log n, which is a much better complexity than n of square root of n. Okay. Initially we were doing with n into square root of n. Okay. Now we are doing with n into log of log n, which is a highly optimized version. So this is the concept of sieve. Okay. So I hope everyone understood it. I can actually start from I square rather than 2 into I, because smaller multiples would have been marked already. Yes, exactly, you can do that. Okay, but I just told you a general form. Okay, general form of sieve algorithm. All those modifications you can do depending upon the problem you are currently doing. I just wanted to make you understand what is the intuition behind sieve algorithm. That is the reason I started with 2 into I. And in fact, you are correct, because all the numbers would already be marked as false, the smaller numbers. So yeah, you can in fact do a I square here as well. Some optimization can be done here as well, but the general fund here remains the same. Okay. So usually this sieve algorithm is done outside the query loop. Okay, in whenever you are doing a CP in competitive programming, you will be given certain amount of test cases. So before you start doing solving the test cases, you before outside the test case you compute all the prime numbers up to a value n. That is, you apply the sieve method and then you proceed inside while you want to do the test cases operations. Okay. Yeah, thank you, Rishit. Yeah, so this was let us pause our session here for today. We will again meet in the next session. Okay. So this ends up our maths essential mathematics. You can look up for other important topics like Euler-Quotient functions and Chinese remainder theorem. So these are important from the comparative programming point of view and are rarely asked in interviews. Okay. So this was just essential mathematics, which was utilized in solving other areas of problems. Okay. So huh. Apart from that, yeah. So we also have a course called Complete Interview Preparation. You will find the link in the description of this chat. And apart from that, you will also be able to, in case if you're preparing for your interviews, you will be able to prepare very well, because that course is extremely well crafted. So aiming for considering the requirements in today's age, how interviews are progressing these days. Okay. So definitely check that course out. And we also have a live mock DSA on every Saturday on this very channel itself on 10 p.m. So in that case, so in that Rishit, you can just Google about the topics. You can also read on CP algorithms. There is a website called cpalgorithm.com, so you can read more about such topics here. But in going in depth for interviews are not required for these such topics, but it is definitely required if you are for online assessments. Okay. the assessment which are considered to be difficult and similar to code forces rounds. Okay, so this was about yeah. And in case if you have any other recommendations or any other type of content that you all want from this particular channel, you can type out your recommendations in the chat box and we will try to deliver those. Okay, so this was about today's session. Thank you very much. So see you in the next session. Website link, okay, I'm sharing. Okay, so you can just Google CP algorithms. Maybe we'll get something. This is, yeah. So let us keep our session till today, and let us meet in the next session then. And if you have any doubts, you can write in the comments. So I'm here for a couple more minutes to solve it out for you. So next, in the next session, we will be picking up with stacks and views, and we will proceed. Okay. Thank you very much.